Today we'll be doing the integral from 0 to pi over 2 of x cubed times the cotangent of x dx. And to start off, we'll use integration by parts. So we're going to let u equal x cubed, which means that du equals 3x squared dx, and that dv equals the cotangent of x, which means that v equals the integral of the cotangent, which is the natural log of the sine of x. So this turns into x cubed, the natural log of the sine of x, from 0 to pi over 2, minus the integral from 0 to pi over 2 of v du, so the natural log of the sine of x times 3x squared dx. And this limit will end up canceling. We can factor out the 3. We have negative 3, the integral from 0 to pi over 2 of x squared, the natural log of the sine of x dx. And from here we'll make a substitution. We're gonna let x equal y over 2, which means that 2x equals y and that dx equals 1/2 dy. The bounds of integration, y1 will be 0 and y2 will be pi. So we're gonna have a negative 3, the integral from 0 to pi. X squared will be a y squared over 4, the natural log of the sine of x, which is y over 2, and dx is a 1/2 dy. So then, putting the constants to the front, we have a negative 3 over 8, the integral from 0 to pi, y squared, the natural log of the sine of y over 2 dy. And then from here, we will notice that the natural log of the sine of y over 2 is the same thing as the natural log of 2 sine y over 2 over 2. And using logarithm rules, we have the natural log of 2 sine of y over 2 minus the natural log of 2. So plugging this into the integrand, we have a negative 3 over 8, the integral from 0 to pi of y squared, the natural log of 2 sine of y over 2 minus the natural log of 2 dy. And distributing that and breaking apart the integral, we're going to have a negative 3 over 8, the integral from 0 to pi, y squared, the natural log of 2 sine y over 2 dy, and then plus 3, the natural log of 2 over 8, and then the integral from 0 to pi of y squared dy. And solving this outermost integral first, we have a 3 natural log of 2 over 8. The integral of y squared is y cubed over 3, and that's evaluated from 0 to pi. The 3's end up canceling, and we have a pi cubed log 2 over 8 term. So now we have a negative 3 over 8, the integral from 0 to pi, y squared, the natural log of 2 sine of y over 2 dy plus pi cubed log 2 over 8. And then from here, we'll use integration by parts again. So we're going to let u equal y squared, which means that du equals 2y dy. We're going to let dv equal the natural log of 2 sine of y over 2, which means that v equals the integral of the natural log of 2 sine of y over 2. And this integral is a special function known as the Clausen function. So that means that v equals negative the Clausen function of phi. And we'll also make the condition that y equals phi. So because of that condition, du equals 2 phi d phi, and u equals phi squared. So using all this information, we have a negative 3 over 8. We're going to have a phi squared and times negative the Clausen function of phi from 0 to pi minus the integral from 0 to pi of v, which is negative the Clausen function of phi times du, which is 2 phi d phi, and plus pi cubed log 2 over 8. So we have a negative 3 over 8, negative pi squared, the Clausen function at pi, plus 0 squared, the Clausen function at 0. And then we're going to have a plus twice the integral from 0 to pi of phi Clausen function of phi d phi plus pi cubed log 2 over 8. And we'll use that the Clausen function at pi and the Clausen function at 0 will all be 0. So all of these go to 0, and distributing the negative 3 over 8 to the integral, we'll end up having a negative 6 over 8. The integral from 0 to pi of phi, Clausen function of phi d phi, plus pi cubed log 2 over 8. And we'll notice that negative 6 over 8 is the same thing as negative 3/4. So we're going to have a negative 3 over 4 integral from 0 to pi, phi Clausen function of phi d phi, and we will use integration by parts again. So we're going to let u equal phi, which means that du equals d phi. We're going to let dv equal the Clausen function of phi, which means that v equals the integral of the Clausen function of phi d phi. And we use the following series representation of the Clausen function. So the Clausen function of phi is defined to be the sum from 1 to infinity of the sine of k phi over k squared. So that means that the integral of the Clausen function will be essentially integrating this sine function. So we're going to have the sum from 1 to infinity of negative cosine of k phi over k times k squared, which is k cubed. So this is going to be in place of our v. So we're going to have a negative 6 over 8 u times v. So u times v, which is negative the sum from 1 to infinity of the cosine of k phi over k cubed from 0 to pi, then minus the integral from 0 to pi of v du, so negative the sum from 1 to infinity the cosine of k phi over k cubed times du, which is d phi, and plus pi cubed log 2 over 8. So we're going to have a negative 3/4. At pi, we're going to have a negative pi, the sum from 1 to infinity, cosine of k pi over k cubed, and we're going to have a plus 0 times the sum from 1 to infinity, cosine of 0 over k cubed. The negatives turn to a positive. We have a plus the integral from 0 to pi of the cosine of k phi over k cubed. That is the sum from 1 to infinity, d phi plus pi cubed log 2 over 8. And 0 times anything is 0. And we also use the following fact that the cosine of k pi equals negative 1 to the k. So we're going to have a negative 3/4 times negative pi, and then the sum from 1 to infinity, negative 1 to the k over k cubed, and minus 3/4 the integral from 0 to pi of the sum from 1 to infinity, cosine of k phi over k cubed d phi, and plus pi cubed log 2 over 8. So we're going to have a 3 pi over 4, and we'll notice that this sum is just negative the eta function at 3. And then minus 3/4. Integrating this, we're going to have a sum from 1 to infinity sine of k phi over k times k cubed, which is k to the fourth. But now phi is being from 0 to pi, and then plus pi cubed log 2 over 8. So we're going to have a negative 3 pi over 4, the eta function at 3, minus 3/4. And we're going to have the sum from 1 to infinity of the sine of k pi over k to the fourth, and minus the sine of k times 0 over k to the fourth, plus pi cubed log 2 over 8. And the sine of 0 is 0, so this will cancel, and the sine of k pi, like we said earlier, will also go to 0. So this entire thing collapses towards 0, and we're left with negative 3 pi over 4, the eta function at 3, plus pi cubed log 2 over 8. And now from here, we will use the relationship between the eta and zeta function. I did a video on this, and essentially it's eta s equals 1 minus 2 to the 1 minus s times zeta s. So plugging in s equals 3, we have eta 3 equals 1 minus 2 to the 1 minus 3, which is negative 2, zeta 3, which is the same thing as 1 minus a fourth times zeta 3. So we're going to have a 3/4 zeta 3. So using this information, we have negative 3 pi over 4 times eta 3, but that's 3/4 the zeta function at 3, plus pi cubed log 2 over 8. And this combining the like terms, we have a negative 9 pi over 16 zeta 3 plus pi cubed log 2 over 8. So now we could say that therefore the integral from 0 to pi over 2 of x cubed cotangent of x dx equals pi cubed times the natural log of 2 over 8 minus 9 pi over 16, the zeta function at 3. And so this is the final result to the desired integral.